Today we're going to be concluding chapter 6 in the multi-agent reinforcement learning book. And specifically, we're going to focus on the policy-based learning methods, which is sort of the last part of chapter 6. But this will also conclude the first part of the book, which is really on like tabular methods in multi-agent learning. And part 2 of the book, which will start introducing things like deep learning and deep reinforcement learning. These are techniques that are needed when you have a very large problem where the state space is too large to what we would say like enumerate the state space, where you can sort of list it exhaustively and collect data and estimates for every distinct state. So right now we're in the situation where we have games and stochastic games that are simple enough where we can sort of write down all of the states and save them in memory. And once we finish this chapter, we'll move on to these learning techniques that require models and parameters that attempt to generalize the state space and make it tractable. So I thought that maybe since we were concluding this chapter 6 section and sort of the entire discussion of tabular methods, that I would do a little bit of like a big picture overview of this. So I sort of wrote out some notes for this that I thought might be a little easier to look at than some of the stuff in the book. So, and for this overview, I'm going to compare some of the things we had learned from reinforcement learning. So if people are familiar with ordinary reinforcement learning, you can make some connections between the topics here. So as I already said, we're looking at tabular problems where we can enumerate all the states and actions. And a common tabular problem that we use as a toy problem in reinforcement learning is a grid world problem, which you can see here, where it could be like a maze or just a grid with a start and a goal state. And maybe there's obstacles in it, things that block your progress. But the idea is to train an agent that learns how to navigate through the grid world and reach the goal, or reach goals repeatedly to maximize some reward. And what I'm showing here is that these transitions with the state action pair, and then resulting in a transition state, and then some reward value here. And this is a common feature of all reinforcement learning problems, that we have this sequence of states, and then the actions. The action selection ends up producing this transition into a new state. And on every step of the transition, there's just this single reward value that we see, and there's a single action selection from the agent. Now, in the multi-agent problem, we also had a sort of equivalent grid world problem, but this was this level-based foraging example where there's basically like multiple agents in what is effectively still a grid world. But the goal is now to do some task, like collect items. Like here, there's some item in this corner and another item in a different part of the grid. And the agents may have to work together. Like in this example, the levels of the agents have to sort of add up to the item level. So they may have to coordinate together in order to collect the item. But the main difference with the tabular problems in multi-agent learning is that now, instead of just this simple transition, now we have this whole joint action transition that occurs. And there is a different reward value for each agent as well. So we can see here, like I'm showing this grid of examples of what can happen in a transition in a single state, right? Where we have to sort of define the action selection for the X agent and the Y agent. This is only for 2 agents. If we had more agents, this grid would be extended in different directions to account for all the different joint actions. And then once a joint action is selected, this is showing the entire list of rewards that each agent would get. So this sort of grid diagram here is also the diagram that we would draw for just a normal form game, in which case this grid would define the game, like a game like rock paper scissors, or there's other of these just two-player games we saw earlier. And depending on what each agent selects, then they get a reward value. And the difference in these in the problems we're looking at now is that as the agents move around and the items are collected, just in this particular game example, that will then change the state. And then that new state will have its own grid with its own effective game. So we're sort of looking at environments where every distinct state that the agents could end up in constitutes a new game state, where the game state, we have to understand what the rewards look like for this entire grid of values. So does that make sense so far to people? What I mean by like a tabular problem?
Yeah, it makes sense so far. The difference between oral and moral, about how there's an action grid between the two agents, or an agent, it would be then a tensor of some sort.
Yeah. So also like in multi-agent learning, like these action selections, the reason why it's a grid here is these are happening simultaneously. So all the agents will select an action, and like one step forward in the game involves like all the simultaneous actions occurring together, right? So it's not like one agent can wait to see what I mean. There are games which are like alternating games where one agent will make a move and then the other. That you know could also be considered a multi-agent problem, but here in the general case, we're looking at problems where we have truly like simultaneous actions. Okay. So, in ordinary reinforcement learning, the goal is to maximize the discounted return everywhere. And the discounted return is some agent going through the environment will get these reward values as these transitions occur. And we're looking at the long-term reward. So like over, an infinite time horizon in general, or until, the environment terminates in some way. We have this idea that given a certain behavior that we would define for an agent, then that agent would achieve a certain value of discounted reward for a given state. And the goal is to find this optimal value function, which is that there is some policy, some set of behavior that is considered optimal, meaning that it achieves the highest possible reward it could have in every state of the system. And for tabular problems, this value function always exists, and like that there is a solution that has this property. So it's a really nice property. Like you always know that there is something called optimal behavior that will produce this. Now, the main difference in multi-agent learning is that instead of maximizing something, what we're usually trying to find is some sort of equilibrium joint policy between all the agents. And by equilibrium, we really mean a situation where all of the agents are getting some sort of reward from their current behavior interacting with all the other agents. And if it's an equilibrium, then no agent can change its behavior in order to improve its own situation. So like if you fix the behavior of all the other agents and you ask, I'm going to assume all my opponents or fellow agents are going to behave the same. Is there anything I could do differently to get a better outcome? And if it's an equilibrium, the answer is no. And the answer would be no for every single agent in the problem. So another way of saying this is every agent's behavior is a best response policy to all of the other agents. Best response meaning like it can't make a change that would produce a better outcome for itself. And like the problem is actually finding a Nash equilibrium can be very difficult It's even difficult sometimes to verify that something is a Nash equilibrium. But in theory, this does exist for most of the types of games that we're talking about. Like there is one or more of these equilibrium solutions. And ideally, we're trying to find them. And there are cases where that may be very difficult or impossible. But nevertheless, like our goal is to find this equilibrium. I mean, there's also questions about whether an equilibrium solution is relevant in all situations. I mean, there is this concept of why an equilibrium is useful. It's useful meaning logically we would hope that logical agents would naturally find an equilibrium solution because it's stable in some way. Like the agents can't deviate from it in any way. So, we're looking for some stable behavior that would arise in a system. Okay. So
I have a question here on
oh
this
yeah,
one.
sure. Uh-huh.
Okay. So on the tabular one, the reward function that you're talking about, or the policy, is it so if we look at that maze example, right? Is the policy for the entire maze from start to end, or is it like at every action when the agent takes an action, it gets calculated and this reward function changes from state transitions every time?
So for a tabular problem, the optimal policy is a global solution. So it would define the optimal behavior in every state. And it doesn't, like, once it's calculated, it has the solution for every part of the problem. And that would also be true for the equilibrium solution in a multi-agent problem. Like that solution would be an equilibrium solution in every state. Like it has to be, because otherwise it could change in one state and then that would affect the solution in other states. So this has to be like a simultaneous equilibrium everywhere.
Makes sense.
Or
Thank you.
an optimal solution everywhere.
So maybe like in a deep learning, like in a forward pass, that's how it gets calculated. Maybe one time for that particular pass. Maybe.
I mean, if you were using a deep learning, I mean, we're not actually. So deep learning you would only use in non-tabular problems, right? Because in a tabular problem, we have this exact solution at every point. The purpose of those techniques is to handle problems that are not tabular. So, but this value function here, like our goal is to actually find this exact value function. This is a distinct value at every state. If this was being represented by a deep learning model, then we would have a function across states, but it would be determined by some set of parameters. And it wouldn't be an exact solution because there'd be potentially an infinite number of states. But the goal would be the same. We're trying to, approximate what this function is, whether we do it exactly with distinct values or we do it with some, parameterized model.
Thank you. Sorry for jumping ahead to deep learning. I know that's not it will come in the phase part 2 of the book.
But if we do use deep learning to find a solution, it would still be a global solution where it would be, a single model that had the solution at every state.
Thank you.
Okay, so those are the goals between the two techniques. Okay, so now in terms of like what do the solutions actually look like? So we know that for ordinary reinforcement learning, there is a unique optimal value function. Whether it's the state value function or here the state action value function, where we can actually work with either one, and the value function is unique, and there is always we can always write down a deterministic policy that achieves this optimal reward or has this value function. Now, there may be many different deterministic policies that all have the equivalent value function, but even any one of them is sufficient to have this. Now, for the multi-agent problem, we can have a set of joint policies for the agents. And if we fix the set of joint policies, we can calculate a joint action value function, which is kind of like the single agent or the normal RL action value function. But now it would have values for the states and for all the joint actions, right? So that whole grid of actions between the agents, and there'd be a distinct value for every agent. So there'd be like a separate action value function for every agent. And then that action value function, that grid, this grid of values in every state, will effectively be like a unique normal form game for that state. So you could think of it as if you're just playing a game in this state with these values, but the values are actually accounting for all the future transitions and everything, all the rewards you get in the future. But once we have this normal form game, then we can look at techniques from game theory to calculate what the equilibrium solution is for that game. So like once we have a normal form game, there in theory is one or more Nash equilibria for that game. And because we're going to have a normal form game in every state, then we're going to have, a different, equilibrium solution for all of the states. But the equilibrium solution for a game is not necessarily deterministic. It can be stochastic, and it can be stochastic in a zero-sum game or in a general-sum game. A simple example used in the book is a game like rock, paper, scissors. The Nash equilibrium solution is actually to select all of the actions with equal probability. If you select any one action with a higher probability, it can be exploited because someone can just select an action more frequently that wins against that action. And I mean, that's a simple stochastic equilibrium. There's games where, you could end up with any sort of stochastic equilibrium. And this is another thing that is very distinct from normal reinforcement learning. Because in normal reinforcement learning, the optimal policy can always be a deterministic policy. And that's not true for these equilibrium solutions. And on top of that, the joint action values that we write down may not even be sufficient to find the equilibrium in a stochastic game. Like in a normal form game, we just have a single game state that we repeat over and over. I mean, the game itself isn't repeated, but to do calculations, we just have this single grid of reward values. In the games we're talking about stochastic games where as the agents make action selection, the state of the game changes and they transition into what is effectively is a new game. And there is a Nash equilibrium for this entire stochastic game that involves the transitions between all the states. And for that type of problem, the joint action values may not be enough to find the equilibrium solution. And there's an example in the book of a type of game that has this property. I'm going to actually mention it in the next page a little bit. But in normal reinforcement learning, the optimal, the value function is sufficient to find the optimal solution. In fact, that is the thing that is unique about the optimal solution, is the value function. And in multi-agent learning, the value function is not necessarily enough to get the equilibrium solution. So in this chapter, we started out with methods that only worked with joint action values and tried to use those to come up with the solutions. And what we're going to introduce shortly is another solution technique that doesn't only depend on joint action values, because there is a limitation to those that we discussed it briefly in the previous meeting, but I'll go over it again a little bit here. Okay, so in order to calculate these exact solutions, the main exact solution technique you learn in reinforcement learning is something called value iteration. It's a very powerful technique. It is a fixed point iteration using the Bellman operator. So once, the fixed point of the Bellman optimality operator is this unique optimal value function for the problem. So we can actually, we have a very easy way of computing this optimal value function, it does require that we have exact knowledge of the problem. So this probability transition function here, this is the probability of every transition in the problem. So it tells you for every state action pair that you could select, all the different possibilities that could happen and what their exact probabilities are. And once we have the optimal value function here, which we can find using value iteration, then we can always take this, derive the optimal action value function from it. This requires knowledge of this, but we already have knowledge of this. And then the way you get the optimal policy from this is you just take the argmax of the action value function. So we just always select the action that produces the highest value, according to the value function. So it's a pretty straightforward process. Now, at the beginning of this chapter, we covered sort of the equivalent method for multi-agent reinforcement learning, and that is value iteration for stochastic games. And for this, we use the same kind of fixed point iteration, but instead of finding the value function directly, what we're actually trying to solve for is these m values, which are going to form that matrix I showed earlier, which has the rewards for every agent for the joint action selection. But in this case, these m values are going to contain like the value for that agent for once the joint action selection happens, where now this value is accounting for all of the future transitions. So these m things, this subscript I is for the agent I and s is for state s, and then these are the joint action values. So for a 2-agent game, this would be a matrix in every state for every agent. And then these values are what we consider is the normal form game that we look at for every state. And then once we have that, we can use a game theory solution like we had talked about, like either a Nash equilibrium solution or the minimax solution is what we had looked at more closely, because the minimax solution, it only applies to zero-sum games, which are only always 2-player games. But the nice thing about zero-sum games and the minimax solution is that there is a straightforward way to compute it. There's a linear programming method. We looked at the method, and it's something that you can actually compute in a reasonable time. For Nash equilibria, there is no general method you can use once you have these m values, even if they were all exact values. It doesn't translate directly into just being able to find the Nash equilibrium. And even it's in general like an NP hard problem. It's not something you can do. So this method and what I implemented in the notes is really only practical for zero-sum games, where the equilibrium concept we're using is the minimax solution, which is a Nash equilibrium, but it's sort of the simplest possible Nash equilibrium that you could have. And this was the technique that we looked at in the first meeting where we were covering chapter 6, is this value iteration method for games. And there was this soccer game example, which I'll show again when I go to the notes. But soccer game was, a zero-sum game. The reason why it's a zero-sum game is because it's really the only game where these techniques work. Okay, and then the problem with the exact solution methods is you need to know the exact properties of the game, all the probabilities, and usually we don't have that information. Like usually we're dealing with problems where we can interact with an environment, we can deploy something in it, collect data, and then we have to use that data somehow to try to compute a solution. So this is what will be called estimation methods, where we collect data and we use the data to do estimates, usually through averaging. So for normal reinforcement learning, the way this usually goes is you initialize a random policy. So you just have an agent behaving randomly in an environment, and you collect data from that policy. And you collect data on these on the the state action values. So we're trying to compute the state action value for whatever policy that we're currently using. And that we interact with the environment, we collect data, we'll use either Monte Carlo sampling or some sort of temporal difference method to update our estimates for this. And then once we have estimates of this, we can always attempt to improve the policy by computing this argmax here, which is also what we do in value iteration. But here we're doing it using estimates, so the solution is not going to be exact. This is all going to be approximate until these values converge. And we also have to use random actions to explore the environment to guarantee that we don't get stuck somewhere. And because this method only works if we guarantee sort of continuing to collect samples from all over the environment. And also the action values that we estimate end up being sufficient to learn the optimal policy. Now, in the multi-agent problem, we also need to collect data from the environment, and we're going to collect it initially from agents that are just behaving randomly in the environment. But now we're going to use the data to estimate the joint action values. So we're going to have, in general, like every agent is going to try to estimate what these joint action values are for itself and for the other agents, right? So we have an estimate for, in a given state, this whole joint action happened, between all the agents. Now, this is going to be harder. It's going to take a lot longer to collect this data because the action space is way bigger, because we have, we're going to have to wait until we observe every agent sort of effectively doing every action in every state. So, this will, you just multiply the number of actions per agent by the number of agents to see how large that space is. But it's one of the challenges of this versus this technique where, usually the action space is effectively much smaller. And then this method kind of proceeds actually very similar to the value iteration method in the first version we looked at, which was minimax Q-learning. And in minimax Q-learning, we collect this data on this, and this is sort of replaces what the M values are for the value iteration method, where we're trying to come up with an estimate of converting every state into its own distinct game. And then we apply the minimax solution in each state to find the policy, but now we're not applying the minimax solution to the exact values for the game. We're applying it now to these estimated values. And again, this is only suitable for zero-sum games. Minimax Q-learning, the minimax solution is only a solution technique that works in zero-sum games. Now, there is an alternative to this, which we talked about at the end of the last meeting, which is doing something called agent modeling. And in agent modeling, on top of trying to estimate the joint action values, we also collect data on the action selections for all the agents. So as we go through the problem, we can count up in every state how often an action was selected by the agents. And we can then use averaging to have a very crude model for the behavior of every agent. So we have this like running tally of what we think the policy is for all of the agents currently. Now, if we have a combination of both an estimation of the joint action values and an estimation of what the policies are, we can actually use that information together to directly calculate a best response estimate for a given agent. So if a given agent is sitting there and has all this information, if it had exact information on this, like if it knew exactly what the other agent policies were and what its own joint action values were, then it could use that to calculate a best response policy. And in equilibrium, we know that in a Nash equilibrium, every agent is using the best response policy already. So the idea behind this algorithm is we keep updating the agent's behavior to use the best response policy, which is according to its current estimate of the other agent's behavior. And then, I don't even know if the book actually proves this, but if this technique converges, like if by doing this, we eventually converge, then what we have converged to will be a Nash equilibrium. So that's why this technique is powerful. Now, it's possible it wouldn't converge. And in that case, we don't know what we have. But even if this technique does converge, like the values will converge to the proper values for Nash equilibrium. But because the policy we're using is always this best response policy, the policies themselves are probably going to be deterministic policies at every given step of the algorithm. So if the equilibrium we need is a stochastic equilibrium, like in rock, paper, scissors, where we have to actually divide the probability between the actions, then we can only see what the equilibrium policy is empirically. Like as the algorithm's running, the actions will change in such a way that if we average them over time, they will match the stochastic equilibrium. But we're not going to be able to like directly see the equilibrium with this best response estimate, because this best response estimate is probably going to not produce this. Whereas in minimax Q-learning, because we're using like a minimax solver on the game, the policy is going to come from the game theory solution, which is going, depending on what these values are, will be able to actually represent a stochastic policy. Like we saw that happen with the soccer game, where like you can actually, in theory, directly learn these stochastic policies. But this algorithm can also be very slow, like minimax Q-learning, because this step where we apply the minimax solution is like solving an entire linear program in every state we end up in the game. And that is much slower of a step than calculating the best response policy using the agent models. So that is a drawback of this technique, is how slow it is. But the main problem with all these techniques is that there are situations where the joint action values are not sufficient to find the equilibrium. And the example brought up in the book is a turn-taking game that has a stochastic equilibrium. So a turn-taking game, you could imagine a game like tic-tac-toe where the players alternate. And tic-tac-toe is a game where a deterministic policy can actually solve the game. So we can actually use action values in a game like that to find the solution, and it's fine. But there's other types of games that are turn-taking. Like in a turn-taking game, I mean that when one agent is selecting an action, the other agent doesn't have a choice to make. So then the agent selecting an action doesn't have to account for it on that particular turn. They know exactly what will happen on the next step. Like it's not a simultaneous action selection. However, over multiple transitions, that interaction could matter. Like it happens to not matter in tic-tac-toe, but the example in the book, I can go to it. Here, I think it's in this section. Yeah, so this is an example. This is just a toy example, but we only need to prove the existence of this. This is a type of game where it's a turn-taking game. Agent 1 selects actions in state 1, and Agent 2 selects actions in state 2. And this is an example of a game where the Nash equilibrium is a stochastic policy. It's derived. This paper is where the Nash equilibrium is derived. But while it might be tricky to derive this, what you can see is that any solution in which the player's actions are fixed, so it's not probabilistic, but like Agent 1 always selects this action or always selects this action, that none of those combinations of actions are in equilibrium, because there's all, and this is, I went over this in the last meeting, but you can see that if you consider in any of those joint policies, one of the agents can make a change to its policy to improve its own reward. So the fact that these types of games exist proves that joint action values alone may not be able to find the equilibrium. Because, yeah, I mean, the reason is if you have a turn-taking game, when you look at the joint action values for a given state, you don't have this grid anymore. Instead, you just have a single list of values, exactly the same as what you have in ordinary reinforcement learning. And in ordinary reinforcement learning, we know that a deterministic policy is enough. And in fact, it's the only type of policy that you can actually find with that type of value function, where one agent just has to look at all of its possible actions and select the one that produces the best outcome, right? It's just a list. It's not looking at the response actions of the other agent. So yeah, this is called no stationary deterministic equilibrium, because the only equilibrium in this type of game is a stochastic one. So the fact that this problem exists means that in order to really solve tabular problems in general, it means that we need to consider a different technique. And that's the technique that's sort of the conclusion of this chapter. And it's a policy method, meaning instead of focusing entirely on action values, we're going to actually look at the policies of the agents and try to directly optimize the policy for the behavior that we want. Now, in ordinary reinforcement learning, we only looked at policy methods much later on when we were looking at approximation techniques, because you don't need to use policy methods for tabular problems. There's always a deterministic policy that you can derive from the action values. But if we're using parameterized functions, then you can use something called a policy gradient technique, where you use sort of a gradient ascent algorithm that continues to optimize the policy to achieve the objective of maximizing the reward for that policy. Now, in multi-agent learning, this is a very different type of policy technique, because, again, we're not using it with a parameterized policy function. We're actually using it in a tabular method where we have an exact policy that we're defining in every state of the problem. And we're going to use a gradient technique to change that policy, hopefully, until it reaches the actual Nash equilibrium for the problem. And you can write down equations that do this, but the difference is that in single agent RL, we have this single objective function, which is the performance of the policy. In multi-agent learning, we have a coupled objective function, because we're trying to find an equilibrium between all the agents. So in general, all of the agents are going to have their own policy function, their own gradient, and we have to find a point where everything is stable. So all of the policies are stable, where like they're actually in an equilibrium. And you can't just simply use gradient ascent to find that equilibrium point. We're going to see that this set of equations, of gradient equations that we have, actually constitute a dynamical system. And this dynamical system has behavior where if we try to like do gradient steps in it, we could end up with a situation where we don't converge to anything. So we have to make some tweaks. We actually need to alternate learning rates and do some things where we change the learning rate on a per step basis in order to converge to something. But we can use these policy techniques to actually find all the equilibrium that we did with the other techniques, plus we can find stochastic equilibrium in cases that we couldn't with the joint action learning methods. So that's sort of like the big picture overview of this, but now I'm going to get more into the details of specific examples and what the policy techniques actually look like. But are there any questions so far on the overview and the different methods we looked at so far?
And just the question that I had, was, between, like, just regular stochastic gradient descent, ascent, and then the infinitesimal gradient ascent within moral, what the tweak essentially is in order to be able to deal with the essential trajectory matrix that might not be invertible, or it might have all real or
yeah. You're talking about the So I'll get to that next. yeah, we'll talk about that in a second, because I haven't actually gone into the details of the policy methods yet. But yeah, that is what we'll talk about next. But are there any questions?
Just a simple question. What determines a large system? You had mentioned earlier on about how there's a simple versus a large system. What kind of a state space would map to small, medium, and large?
Well, it really, I think. So to use tabular methods, we need to store a distinct value for all the state action pairs or state joint actions. So it really just comes down to how much memory you have. And also, even if you have enough memory, there's a point where it just might be too, I mean, it's probably just memory, because honestly, like you could say it could get too slow at some point, but it's still probably going to be, if you actually can represent it in memory, it's still probably going to be faster than any sampling method, just because the exact solution techniques are really efficient. Like all the fixed point iteration, it works great. Like you're not like wasting any time with samples. So if you get to the point where you can't store that many values, which happens pretty quickly, like you can imagine, just it's very easy to have a state space that blows up where you just can't store all of them.
But the flip side of the memory is the number of processing, GPU, whatever you want to, TPUs, whatever. Doesn't that map into the size of the state space as well, or is that orthogonal?
Well, I mean, yeah, like you have to operate on all of the memory.
Right. So yeah. It's both then what you're.
But I mean, suggesting. I'm saying like you have a given amount of compute and memory. I would say if you can fit everything in memory, like so you could attempt to do an exact solution technique, then that's probably going to work the best with the compute you have. If you instead try to, use an approximate technique with sampling or whatever, like it's just going to be way less. There's way more that can go wrong with the other techniques.
So okay, I got it. I got it.
Yeah, usually the thing stopping you from doing an exact solution technique is just you can't write down the whole state space.
Yeah, I was just trying to understand what the dependencies are. I think you answered my question. Yeah. Thank you for that.
Okay, great. Got it. Oh yeah, so I mentioned that for the first technique we looked at, this minimax Q learning. Oh, by the way, this was the soccer game we had been looking at earlier in the chapter. What I'm showing here, this grid, these are sort of the game values that are being learned. So this tells you in the soccer game, there's 5 actions that can occur, which is moving in 4 directions or staying still. So this is showing the joint action value for one of the agents. And actually for a zero-sum game like this, you only need to show one set of values because the other agent's values are just the negative of this. Because that's one of the properties of zero-sum games, is that the reward of the second agent is always just negative the reward of the first agent. So because this is a zero-sum game, we can use either an exact technique or minimax Q learning. This is showing, I guess, the actual minimax policy here in these states. And in this game, there are, like here, this is a case where the minimax policy, sorry, this is a very long episode, is deterministic, right? Where like the minimax policy is actually a single action, right? Which can happen in these types of problems. But the thing in multi-agent learning is there's also situations like this where with these, if this was a game, like not a game that went on, but just a single game defined by this game matrix, then this is the minimax solution. You can see that it's a solution where the values are stochastic. Just like in rock, paper, scissors, you have to select all the actions with 1/3 probability. This is a more complicated solution where, each agent has 2 actions that have to be selected. And we had, so I'm not going to go into it too much, but we already looked at this last time where, the minimax solution has this property where it can't be exploited by anything. So like you can't, the only solution that performs well against the minimax policy is the other minimax policy, and you can't do anything to exploit it because it's already, the best response to the optimal policy. And in order for it to have that property, it needs to have stochastic actions. And we saw there's other techniques where you can learn solutions that are not stochastic, that are deterministic. And any deterministic policy you find for a game can have a situation where you can train a policy against it that can exploit it and win 100% of the time. And that's what happens in the soccer game, where something looks like a good policy, but it's not the minimax solution. And as a result, and same if you're not in an equilibrium solution, something could be trained in order to exploit it, right? Because the only type of solution where you can't deviate from it to improve some stuff is an equilibrium solution. So we did that with minimax Q learning, and then with agent modeling, this is what I was talking about, where we use this equation to calculate the best response policy using the current estimates of the other agents' policies. And we collect data. This is just a count of the number of times this action has been selected. So we're just having a simple average as our model for the agent, for the agent models, right? So this is just, the agent model is just simply, counting what we think the probability is of the agent's actions are. And then we can use this to also try to, so this is what we went over at the end of last time, how this algorithm works. Maybe I'll show quickly in the book how this algorithm works. So this is the joint action learning with agent modeling. We update these Q values, right? These are the joint action values for the game. And then we also have to, have the agent models. And then once we have that, we end up computing the best. Here it's sort of like, this doesn't actually say how to use the best response policy, but it's the equation I showed earlier, where we can use this information of the agent models and the Q values to calculate the best response policy. And then this Q value update actually looks a lot like what we have in normal reinforcement learning, where this is like a temporal difference update, which, should, once the values are converged, this update should produce no change in the value, which is the meaning of convergence, which is also the same reason why the Bellman, like the fixed point iteration, works. So we're just trying to find a point where these values are all self-consistent. And then, agent modeling. So the other thing about agent modeling that I mentioned, so for this technique, like minimax Q and for value iteration, we could only use this for a zero-sum game, right? Because we have to actually at some point take this game matrix and compute the minimax solution, which we can do with a linear program. And in a general sum game with multiple agents where there's a Nash equilibrium, we can't just simply find it. It's a very hard problem. We essentially have to exhaustively just search through all the possible equilibriums until we find one. And that's really not feasible to do on a per step basis in this type of algorithm. Now, the difference with agent modeling is that while we can also use it to solve zero-sum games, we can also use it to solve general sum games, because the best response we calculate just needs the agent models. It doesn't need to do this game theory solution. And we're just sort of hoping that it converges, because if it converges with all the best responses, then we know we have found a Nash equilibrium. So you can use it on the soccer game. Here's just an example of a learning curve for it. When this converges, like this value should be 0, meaning that, both agents are, like neither agent is actually winning, because if in the minimax solution, we know that the win rate should be, like no agent should win more often than the other agent. Otherwise, it wouldn't be a minimax solution. So here are the statistics of this joint action learning. And it's like pretty close to even, actually. Playing against itself, it wins. Half the time, it still has like a slightly, like a non-zero reward here. And then versus the minimax policy, we can see that because this is a technique, an estimation technique, if we actually play this against the exact solution, this has, a negative reward, because, the minimax solution will always outplay this and do better. But if we play it against something like the random policy, you can see it did learn, something good, because it's winning 98% of the time, and it has, this positive reward value, indicating it's doing somewhat well. Oh yeah, and then again, like I said, the other thing I had showed in previous meetings was the optimal opponent. So what this does is it takes the policy that you've learned from the multi-agent learning process, and then it just attempts to learn an optimal opponent against that, right? So we have one agent, and we're saying, let's fix that agent. It just stuck. And then we're going to try to exploit it as much as possible. So that's what this does. And we can see that against the optimal opponent, we were able to find an optimal opponent that wins, 80% of the time, and it wins 90% of the time when it starts with the ball, right? This is for the first agent starting without the ball. So this is definitely an exploitable strategy, indicating we didn't find the minimax solution, which is also what we would expect from any technique like this. Like if we're collecting samples, estimating, we're never going to find, the exact minimax solution. We can only find that with something like value iteration. And then you can also use it on this level-based foraging game, which is sort of the grid world example I used. These are learning curves that the book has some learning curves on this, comparing different techniques. They claim the joint action learning method learns pretty well for this. But again, there's a lot of hyperparameters to these techniques that affect how well it does. So, I'm not sure exactly. I actually found that the method they're sort of trying to criticize in the book, which is central Q learning, which treats it as a single agent problem, which you can do with a cooperative problem. So if you have a multi-agent problem, which is cooperative, meaning all the agents are sort of attempting to get the same reward. They all share the reward, whatever it is. You can just take the action space and just say, imagine you had a single agent controlling everyone else. That single agent has to decide the actions for all the other agents. So it's a pretty big action space, but it's still a single agent RL problem. And we can solve it exactly. We can use Q learning. We can use all the techniques from reinforcement learning to solve that. And it could be slower because the action space is big. This independent Q learning avoids that by training each agent separately, which can also work for these cooperative problems. And, this is not quite the optimal solution here, but, they all eventually find a pretty good solution to this problem. But the thing that we can do that's new with the agent modeling is we can actually look at a general sum game. Oh, wait, sorry. Actually, first, before that, the book does have this example of rock, paper, scissors to just show what this looks like. I mentioned rock, paper, scissors is not a general sum game. It's a zero sum game. And these stars here show what is the minimax policy for both players. It's sort of divided here. This is only showing rock and paper. So, right, there's 3 actions, but we only need to show the probabilities of 2 actions because the third will just be 1 minus the other 2. And this is the 1/3 probability solution, right? So this is showing what the policy is empirically during this agent modeling, right? It's basically showing what the models are for each respective agent. So as the learning process occurs, the empirical distribution of actions should be converging to the equilibrium value here. And that is more or less what happens here. Again, the hyperparameters like the learning rate, the exploration rate affect a lot how well this works. But you can see that it moves sort of in jagged turns into the policy. It's not a smooth convergence because the best response policy is going to basically choose one action until the values change enough that it causes it to switch to another action. And that's what's happening here is one action is being selected over and over, and then suddenly a different action is selected, and then it changes the probability. So these end up moving in sort of a triangular pattern because there's 3 possible actions for this problem and empirically converging to this. Now, we can also use this technique for a general sum game, which we couldn't do with the techniques we talked about so far. And that is what I'm showing here. Now, this is a very simple general sum game. right? We have two reward matrices. This is for two agents, and this is the rewards for the first agent, given the 4 different combinations of joint actions, right? Each agent has 2 actions. And then these are the rewards for Y. So I can change these values to whatever I want. And also, because this is a simple 2-agent, 2-action game, this is one of the few examples where we can actually calculate the Nash equilibrium. Exactly. It's only because the problem is this small. Once we get to 3 actions or more and two more than 2 agents, we can no longer do this easily. So what I'm showing on this diagram here is, because there's only 1 action for each agent, we can represent the policy on a grid where the value on the x-axis is the probability for agent 1 selecting action 1. And the y-axis is the probability of agent 2 selecting action 1. And we only need 1 value, right? Because the other action is just probability is 1 minus that. Okay, so for this game here, these values, there happens to be 2. Hold on. There are 2 equilibrium. Wait, 4, 0. So this, sorry, in one of the earlier meetings, we looked at these different 2-player games, actually. And there's a list of sort of more interesting ones. So I believe this game, this is the Stag Hunt game, where there's, and again, because you can get an exact solution, this game has these properties where there is a deterministic equilibrium, meaning that like the equilibrium is where there's a probability of 1, both players do the same exact thing every time. And there also is a single mixed equilibrium with these where each agent selects action, the first action with a 2/3 probability. But we can also, we can change this game to something else. And we can see here that this algorithm, I'm showing this trajectory of the empirical policy, and it is approaching this pure equilibrium, right? We don't know which equilibrium it's going to find. We can't control that with this particular technique, right? There's also one in this corner. With this initial point, this is what it happened to find. If I keep running this repeatedly, we can see it takes different trajectories, but it's still always going to this equilibrium. Now, this is the mixed equilibrium, which it almost never reaches. It turns out if you have a game where there's both pure and mixed equilibrium, almost every technique we're going to look at, it has a really hard time finding the mixed equilibrium, and will always end up much more easily finding the pure equilibrium, like it's doing here. But here, I'm just going to change this game to something a little different. So this, even though this works for general sum games, I'm going to first make this a zero-sum game here. This is what's called a matching pennies game. And so the properties of this game are, the first agent wants the actions to match, right? So basically it wants, whichever action it picks, it wants the other agent to pick the same action. And for agent 2, it wants the opposite. It wants the actions to not match. So this is the reward matrix. They're just opposite each other. So this game happens to have an equilibrium. Well, actually, I could add, if anyone looks at this game, so basically, you're both going to pick actions simultaneously. And, one agent wants to match, the other agent doesn't want to match, right? So does anyone have an idea of what the equilibrium solution is for this? Again, this is a zero-sum game, right? If you look at the rewards, they're always negative the other. So this has a minimax solution. And it does have a stochastic minimax solution. But you can think of it, kind of compare it to rock, paper. This is like the sort of 2-action equivalent to rock, paper, scissors. In rock, paper, scissors, we have, one action beats the other, but, there's
the best assumption that I could, think of is that, in that case of having 2 subsequent coin flips where, well, not coin flips, but basically picking a number of 1 or 2, essentially, that it would probably converge to 50-50 probably, unless I'm wrong. Because I thought that because of that, then since if one of the actions is preferred, then agent Y would have problems because agent X would mimic the policy of agent Y probably.
Mm-hmm. Yeah, so your instinct is that they would both have to select one or two with equal probability, because any deviation from that would be exploitable. And yeah, that is the right instinct. It's the same kind of thing with rock, paper, scissors, where we can't prefer one action over the others, because if we do that, our opponent can just look at that and be like, okay, well, I'm just going to select the action that wins against that preferred action. So if we look at this, there's one mixed equilibrium for this. It happens to be at 0.5, just like Dimitri said. And we can see how this is empirically converging to that over time, right? So this algorithm appears to be working. Again, it's doing it in these jagged steps, right? It's switching which action abruptly. So we have this diamond shaped convergence. But the nice thing about this is I can change this to be the same, almost the same kind of game, but to not be a zero-sum game, right? Like if I make this value like -5, this is now no longer a zero-sum game, right? This first one is now not a value of 0, but a value of -4. So now this will have a different equilibrium point, right? It's over here, right? Here's where the mixed equilibrium is, 0.25 and 0.5, because now this is no longer a zero-sum game. We've introduced some asymmetry into this, but there is still now a non-trivial mixed equilibrium, which this is a Nash equilibrium, right? It's not a minimax solution, but this algorithm is able to converge to the Nash equilibrium. Now, of course, we would expect it to work because this is a simple enough case we can solve it even by hand exactly. But it means that in theory, this algorithm can find Nash equilibrium in more complicated games. So does that make sense? Any questions about this? Or the game matrix and the equilibrium point?
So what is the difference between the mixed and pure equilibriums?
This only has a mix. Wait, so this particular game only has a mixed equilibrium. If I change the values more, now it has a pure equilibrium here and a mixed one, although it's possible that all of these are equilibrium now. But yeah, so now the algorithm is converging to this pure equilibrium rather than the mixed one. But whether there's a pure or mixed equilibrium, it just depends on the game itself. In general, we can have, a combination of them. But there's always at least one. And it's what, here, we change the game, right? So Prisoner's Dilemma is an example of a game that only has a pure equilibrium.
So would the difference between the pure and mixed equilibrium be essentially if it hits just some corner of the problem space?
Oh yeah. Like they have different properties. So the pure equilibrium in this type of game, there's only 4 pure equilibria you have to check. You're basically just checking if any one of these are any corner of this grid is an equilibrium, meaning like you check if there's an improvement you could make from changing the action. And if not, then it's an equilibrium. If not for both players. I mean, this problem's small, so we are effectively exhaustively searching the pure equilibrium space. But it's not a very big space, so we search it. Yeah, in order to find, so actually, it's a good segue into the policy method discussion, because the Nash equilibrium, in the case of a 2-player, 2-action game, we can actually write down equations to calculate mixed Nash equilibrium. And actually, I had done this in a previous meeting without realizing it was going to come up again with this in this chapter. But these are my notes from that meeting where we looked at this game. So this is just a general 2-player 2-action game, right? The game is defined by 8 values, right, which are the 4 joint action rewards for each player. And then what you can do is you can write down the reward for each player under a given policy, right? Where the policy here, X and Y, this is a number between 0 and 1. And it defines the policy for the player where it's the probability of the first action, and then the second action is given, it's derived from the first action. So you can write down the return for each player. And then you can also say, what are the equations for a Nash equilibrium? And really in order for it to be a Nash equilibrium, it means that no player can deviate from its action choice and have an improvement. But that's pretty easy to formalize. We can just write down the partial derivative of each return with respect to both, X and Y. And this is the result. Now, if we have a Nash equilibrium, it will have the property that the partial derivative will be 0 for both players at that policy. And it results in this equation where now we have X and Y. Now, this means that for any game like this, we can just directly solve for the Nash equilibrium. Now, it seems like now there's a single Nash equilibrium. However, there's another little wrinkle to this. But can anyone have an idea of what the problem could be with this calculation? Where we're trying to find the point where the partial derivative is 0?
Well, you don't know if it's a relative minimal or max or a global minimum or max, right?
These equations happen to have a single global optimum because they're linear. So we don't have to worry about that. It's actually why when we solve for a mixed, a general, which in general could be a stochastic Nash equilibrium, we only get a single value for X and Y.
Okay.
So anyway, so the problem is that what if the value we get for X and Y here isn't between 0 and 1? I mean, these have to be probabilities, right? We're trying to find the policy. So actually, if you have a problem that just has a pure equilibrium like the prisoner's dilemma, what you'll find is that if you try to compute these values for it, they won't be between 0 and 1. Which means that there is no mixed Nash equilibrium. And instead what you have to do is this, which is check all the corners and say there happens to be a pure equilibrium just means X and Y, they're either 0 or 1. Does that make sense to people?
So are you normalizing?
No, there's no
you basically a bounded optimization problem instead of just a pure optimization problem, because the pure optimization problem would be outside of the space of the solution.
Yeah, this is unbounded. Yeah, exactly. So basically you end up with a mixed Nash equilibrium when the shape of these curves have an optimum in the probability simplex.
But then, since you have, basically a bounded optimization problem, couldn't you just find like Lagrangian or something like that, or the dual problem?
Yeah. Actually, we'll see this with the gradient method, but you can actually just use the same gradient method and just bound it inside the probability box, and then it will also end up converging to the pure equilibrium. Yeah, actually, it turns out that the pure equilibrium are not hard to find. The things that are problematic are when you do have a true stochastic equilibrium, and where you have to make sure that you actually have a way of converging to it. So, I mean, for this simple problem, right, we can actually just calculate x and y directly. But we do have these gradients. So for a more complicated problem where we can't just solve it exactly, perhaps, we can use the gradients to instead iteratively compute what the policy should be. And that's the idea behind the policy gradient methods. So let's just look at policy-based learning. So here I'm just recreating there's a slight difference in notation here. Right here I'm using alpha and beta for the policy. So this is the notation used in the book. So we have agent X and Y. Its policies are defined by alpha and beta. And this whole thing is derived for this simple case again, where we have two agents, two actions, and we have the partial derivatives here. And the idea is, well, let's say that we initialize some value for alpha and beta. And then on every step, we just do a gradient step. Okay, so we add to alpha, some learning rate times its gradient. And yeah, we have all the information here, at least for the 2x2 case, to calculate these gradients. We happen to already, for this simple case, we happen to know the solution already, but this is just a test case. Like, we can see if it's actually converging to the correct solution. So this algorithm, like if we just attempt to do this looks like just a gradient descent or gradient ascent algorithm. But normally when we do like stochastic gradient descent or ascent, we have a single equation, like a single gradient update. Here we have two gradient updates, and they're coupled together because this has terms in it, this partial derivative, that depend on beta. So unfortunately, this is not just a simple matter of following the gradient and arriving at the optimum, even though there is a single optimum for this, like a single, mixed equilibrium. But now we're sort of in the realm of dynamical systems theory. And we can see, so I tried to, like, the book has different diagrams and things with these trajectories. I tried to make sort of a general visualization where we could just write down any game. And actually, let me just change this to the one I showed before, because it's simple. We know where the equilibrium is. I'm sorry, negative. So this is like the matching pennies game I showed before. Okay, so here's the problem now. So here what I'm showing is, let's say, and I have these parameters here that I can control. So what this is showing is, I'm sort of skipping ahead where it turns out we have to alternate the learning rate. But what I'm showing here is a situation where we just use the same learning rate for both alpha and beta on every step. So if we do that, and we just follow this trajectory, if we initialize a policy here, or I can also change the initialization point to whatever. So we end up with a trajectory that just goes around in a circle around the equilibrium. This is also a case where the equilibrium point is in the middle here, which it turns out is the important case that we need to figure out a way to converge to. The other types of problems where we have pure equilibria that exists on the corners, where this star is outside of the grid, those actually will, as long as we bound the update in this grid, they will actually converge to one of the corners, just because it doesn't have this same problem. Where we really have a problem is this situation, where we have some equilibrium, and I can also make it asymmetrical again, right? Where now it's here, so now we're going in ellipses around this equilibrium point, and it's not converging. Now, what I'm showing here are different trajectories which do what is the important point made in the book, which is that you actually need to use a different learning rate depending on what part of the trajectory you're in. And here I'm going to do that now, where I actually make this learning rate higher than this one. And what that will do is cause this trajectory now to spiral in to the equilibrium point. And this spiral is actually formed of piecewise ellipses that are connected together that each have a different curvature. And if I make it a little more extreme, you can sort of see the ellipses. You can see the piecewise connections a little more, where it gets a little more jagged, but you don't actually need it to be that extreme. I mean, this will converge also if this is only just double the value, right? It just takes longer. Like here, it needs more steps to reach the convergence. But this diagram is sort of equivalent to what is shown in the book here, where we have.
Is that because of like the nature of how basically it ends up being in basically a well based on the step size being the limit, and then it gets stuck on.
Oh, you mean why does it form circles?
Well,
yeah, I mean so the reason for this, which like the book doesn't go into this either, but these are well-known properties from dynamical systems equations, that this is like the simplest dynamical system that you can study, right? It's just these two coupled equations with two variables. And yeah, like the property of this F, right? F is this matrix here, which is derived from the values here, end up controlling this. So this case, both of these cases actually won't have a problem converging if we use this sort of bounding box method, where we do the gradient steps, but if it tries to go outside of the square, we end up just projecting it back into the probability space. And that will end up naturally inching its way to the proper pure equilibrium, or the value in the corner. Yeah, like you can see here, these lines are sort of, if you end up following this trajectory into the floor here, and then you keeping it within the bounding box, it will just sort of move its way slowly into this corner. I could show that also with changing some of these numbers. But this is the case where really the bounding box isn't helping, right? This is staying like within this bounding box, and we really have to find this point in the interior of the space. So for that, you need to alternate the learning rates, and that's what this win or learn fast method is, where what you do is, if the current value you have at the current policies for you and your opponent are better than what you would expect if you were in equilibrium, or have the equilibrium policy against your opponent. Sorry, see, this is like, this E is the true equilibrium that you're trying to reach for yourself, right? But the beta K here is like, this is a little weird because normally we look at the value you achieve at equilibrium. But in this case, this is not the value at equilibrium. This is the value where you might be in equilibrium, but your opponent is not using a policy that is in equilibrium, which means that there could be a value of alpha that you pick that actually happens to be better against your opponent's current policy. Then you use one learning rate, and if this is less than or equal to this value, then you use this a higher learning rate, right? I could show here that this method actually fails if you reverse this. So if I make this 1 and this 2, so now, right, instead of this L max should be a higher value than this. And this ends up producing a trajectory that actually spirals out and ends up trying to leave the bounding box and then getting stuck in it. So this does require this relationship between the two. Of course, this isn't derived in the book, and it's probably a lot to go into. I myself didn't look at all the details of how these alternating learning rates work, but it is something from this particular dynamical system, the way it works. You can get this spiral convergence trajectory if you alternate the learning rates like this. Of course, doing this requires knowledge of these equations and of alpha and beta, which in general, we don't have these exact values at our disposal. But this is just a toy example to show an example of, like, at a bare minimum, we need to have a way of dealing with this lack of convergence here if we just use a single learning rate. Yeah, like we can see here. I'll make this a little closer in, where we end up just going around the equilibrium value. And this is just showing, I have different initial starting points here to show a bunch of these spirals and what they look like. But if I change this game to something, I'm not gonna like make it an exact game here. but something where I need to change this so that there's, oh yeah, okay. So now the game only has a pure equilibrium in this corner. There's no mixed equilibrium because I changed the properties of the game. And now we can see that this is finding the right value. I'm truncating these trajectories so they stay in the square. And notice now that I didn't actually use the alternating learning rate. I'm using the same one. So this is not a problem when we have a pure equilibrium like this, keeping these the same. But in general, we need to have this rate be higher than this one for this algorithm to work. Yeah, because we're primarily interested in this technique for learning stochastic equilibrium, right? Not for the pure equilibrium. The other joint action methods have no problem learning those. Okay. So actually, okay, so this is showing the actual, like the theoretical, right? This is like we have all the information. We're actually using these equations to perform this algorithm with these values. But what we're actually interested in is a technique that we can use with sampling. And it's inspired by this, but the technique in the book is this win or learn fast policy hill climbing algorithm. And it's an algorithm where we still have to learn the joint action values because it turns out we're going to need to use them in the calculation of the gradient. And we're going to keep track of the, so we're initializing with random policies here. And the Q values we're updating the same as we were doing before. In this case, we actually only need, each agent just needs to store action values like we would do in single agent RL. These don't have to be joint action values. Because instead we have each agent has, it has two things. It has a policy. We're keeping track of its average policy over time, which we're also updating with a sort of a temporal difference method. And the policy, this is the count, or no, sorry, not a temporal. This is just a way of averaging over time without recomputing the sum, right? We're keeping track of the count of how often a state has been visited. And then, yeah, this is like a way of averaging the empirical actions we've observed. And then this is the gradient policy update, which is using this equation. This triangle term is defined earlier in the book, but it's defined here. And we have two different values we're going to use where we have one learning rate if we perceive that we're winning in the current state and the current policy values that we believe each agent is using. And then there's another learning rate for losing. But here again, we have to estimate whether we're winning or losing with this equation. And this is another kind of hack because we don't have access to all the information, but this is why the average policy over time. So we have this sort of long running average of the policy, and then we have the current policy. These two equations are computing the same thing. They are computing in the current state, given the policy, what the agent thinks its value is for all the different actions that it could select. But for one of the calculations, it's using its average policy over a lot of time steps in the past. For the other calculation, it's using its current policy. So the idea here is we're going to use all these estimates as a way of, like, if the current policy version of the calculation is higher, then we're assuming that we're sort of winning or we're doing better than we have been doing in the past, looking at the type of policy we were using over, older time steps in the system. And then we have this, like all these sort of things actually are to make sure that the probability stays normalized here. This like sort of minimum operation, because again, we're not actually forcing the policy to be a probability like through some other method. We have to make sure that the value update that we do with this delta has to actually preserve the probabilities correctly, or we'll end up with just a distribution that is not really a probability distribution. And that's what's being done here. But again, like the details of it are kind of a little complicated. Actually, this is also assuming that there is only one greedy action here according to the state value function. And if you have multiple actions that you consider, you have to actually change this equation for the action space to make sure that the probabilities are normalized correctly, because otherwise you're not going to be adding and subtracting the correct values to make sure the sum is 1 at every point in the state space. I'd say what is very clear to me in the book is this sort of derivation of these dynamical systems equations is very clear from, the simple 2x2 problem. There's not really a full explanation of how this, I'm sure if you look at it longer, you can probably see how these, simplified equations that we derived up here makes itself consistent with the algorithm used here with these delta values. The thing that we're really doing here primarily is checking whether we believe we're winning or losing and changing the learning rate. This part is really just to make sure that the probabilities are correctly normalized. The actual details of what, I guess for the gradient update, we just need the direction to be correct. But I don't know. I was mainly, in terms of learning, I was mainly interested in just deriving how these equations work and how the trajectories work. Just sort of take it for granted that this win or lose fast algorithm is a way of applying that to a case where we're just collecting samples. And we can try to verify it with different problems. So this is an example again of the rock, paper, scissors game, using this, really collecting data using a variable learning rate. And if we compare it to what I showed with this joint action learning, and also here, where we had these sort of jagged changes in the policy, the empirical policy. Again, because here we're not directly optimizing the policy, right? This is the joint action learning where we are deriving an empirical policy from the samples collected and the joint action values that we're using. In this algorithm, we're directly optimizing the policy, so we actually have a chance to have this smoother trajectory where we do like a true gradient update that is just like we showed in the toy examples, is able to sort of spiral in to the correct values. Our goal, like the ideal trajectory we would have with this technique is to have policy trajectories that look like, what we had here, where we had the values spiraling in to the equilibrium point. And that is what we see with the rock, paper, scissors example. So I have it doesn't look quite as clean in my example. I also use this to train on the soccer game. They sort of abandon this example later in the book, but like you should be able to use this same, wolf, right? This wolf sensor, win or lose fast, policy hill climbing. And you should be able to use it for the soccer game. Here, we appear to have converged to a value pretty close to 0, which is hopeful for equilibrium. We can see, actually, this policy is pretty close to the minimax policy we found here, right? Because here, playing this version against the minimax policy, we can see that the value is very slightly negative, but overall, it's pretty close to 0, meaning we've achieved something pretty close to that. And again, against the random policy, it does extremely well. We can see, this is one of the highest rewards I got in this game against the random policy. I think even higher than the minimax policy had. And then also against the optimal opponent, of course, like this is exploitable, right? There is an opponent here, which its reward against the optimal opponent is negative, but it's not that bad. Like it is closer to the minimax policy. And we can see also that the number of steps in these games, this is like 700 or something steps. So it is managing to hold out a very long time against even an optimal opponent. So while it is exploitable, it appears to be, it's done a fairly good job at finding an equilibrium solution. Also, this is a level-based foraging game. I showed it, this should also work for that, even though for that game example, which is a cooperative game, you don't need to find an equilibrium solution. But here's an example of it on the rock, paper, scissors game. We can see again this sort of like, it's not a perfect spiral shape, but the shape is somewhat smooth, this trajectory, right? It's not the same sort of jagged, sudden changes in policy. At every point in the learning process here, it is at like using a genuinely stochastic policy for this as it approaches the equilibrium solution. And again, we can also use this in the same for any arbitrary 2x2 game. So this is again the matching pennies game from before, although I made it asymmetric again. So here now the equilibrium point is over here, and here we can compare the results. So this is actually the Wolf IGA. It looks a little messy actually. I mean, perhaps this example is too simple, but I mean it is like, kind of randomly moving around the equilibrium point. This again is the joint action method where we empirically do it and we have these, jagged lines that switch the policy. But again, if we change this so there's a pure equilibrium, hopefully that, yeah. So now there's only a pure equilibrium in this corner, and we can see like this is the theoretical like IGA, trajectory for it. And then both of these techniques are able to successfully, approach the pure equilibrium as well. So yeah, we verified that. Yeah, okay, hold on. So the reason why we need this algorithm again is because like there are situations that are brought up here with the limitations of joint action learning where like we need a technique that can actually find a stochastic equilibrium in a general case, even if the game has states like this, where one of the agents doesn't have any action choice to make. And this algorithm, the policy hill climbing algorithm, in theory, can do that. But we can verify all these trajectories, right? This is a case where in this example, there's this mixed equilibrium. And again, like to find the mixed equilibrium, the way this technique finds it is it follows this dynamical system, and it has a way of forcing this to spiral in to the equilibrium point. So that, I mean, there are other things in this chapter, but honestly, most of them are not that important. Like there's this discussion of no regret algorithms, but again, they don't really have very nice properties. This no regret learning, they show it with the rock, paper, scissors example, and how the policies, again, it has the same sort of jagged performance change we have with joint action learning methods. So, I mean, we might as well use one of those. And then during the learning process, again, like the policies are always in these extremes. They only converge empirically. And then, yeah, here's showing like things alternating over time. So I'd say these types of methods don't have much of an advantage. You can read the section in the book, but there's a reason why there's no, pseudocode provided for these algorithms, because, they don't really have any advantage over anything else. So again, like this sort of concludes the discussion of problems that we can solve in this manner, where like the functions we're talking about that exist in the pseudocode, like the policy function here, these are numbers, right? There's a distinct number for each of these inputs that we give it. Same with the Q values. It's going to be true for all the algorithms in this section. And to deal with more challenging problems, we're going to have to move on to the techniques in part 2 of the book, which involve deep learning and, more gradient methods. But now we're going to use the gradients to update parameters and a function that is approximating some of the things we have here. So that, I guess, next time we'll start looking at some of the stuff in part 2 of the book. Again, I don't think we'll cover chapter 7 or 8 very much. I mean, maybe 8 we'll look at a little bit because it's looking at deep reinforcement learning. But again, like we covered most of this already in the Sutton and Bartow book. And then this is just an overview of deep learning in general, nothing to do with reinforcement learning. So we probably won't look at this at all. Yeah, and just assume that people are already familiar with the basics of how deep learning works. But the main focus will be chapter 9, which actually starts getting into multi-agent deep reinforcement learning. Yeah, unless there's like a particular part of deep learning or the ordinary deep RL that people are interested in looking at, then we could, always look at it. But I haven't looked at it that closely yet, so I haven't decided exactly what we're going to do next time, but we'll definitely be moving on to part 2.
I have a question, if I may, Jason. As far as the models that support this kind of work, whether it's on Hugging Face or on Git, where would we find something that is something that we can play with that would be along the lines of what we're describing here for?
Do you mean like the stuff we've done so far?
Well, not
Or
just so far, the bigger picture
laters?
for the book itself and just for reinforcement learning.
Yeah. So the book has a GitHub repository, the authors of the book, which provide code that I think it does use Torch, I think, for the deep learning stuff.
PyTorch,
and they have examples. They had a workshop where they did some coding examples and things you could play with that again was pretty much entirely focused on part 2 of the book. Like their code base. Now the code, like actually this stuff in this notebook is on GitHub as well that I've written. But like, so I implemented like these algorithms. These are not the deep RL algorithms. Like these are the tabular methods. And for these algorithms, there aren't like, if you just look around at like general like repositories or tools, there isn't that much focus on writing these algorithms. I think I didn't look closely at the book authors repository to see if they have, I mean, they must have some of these algorithms in there because they did generate the plots in the book in part 1. But I would say like most of the code you'll find out there is more focused on like deep learning techniques and integration. I know
would that cover like deterministic and stochastic policy or
yeah, I mean
gradient methods or value functions or Markov decision problem. What are you referring to?
So for single agent RL, right, there's a whole world of these algorithms, and I don't know of a great repository for that. I know that so from like my repository that you can find, which we did like for the Sutton and Bartow book, in that I did like implement all that stuff, including like deep learning versions of the algorithms in the book.
Okay.
So you can find it on my GitHub, but it's not going to be like using Torch and all these like stuff on Hugging Face. It's much more, it'll have like just all the algorithms sort of from the ground up, starting at the most basic level. So what you'll find more from like Torch is maybe like it's mostly a deep learning package that handles different architectures and gradient, automatic gradients. And then there's some reinforcement learning stuff maybe included in it, but it's sort of more of an afterthought. If you want stuff that really covers like all the RL techniques and like, tabular methods and like, mixed and pure equilibrium and game theory, I'm not that familiar with anything that does that very well. But if you want all the algorithms related to single agent reinforcement learning, you can look at like the repository I have, and there's also some other RL packages. And of course, the moral stuff for me is still like a work in progress. So I've only like, this is all I've written so far is like the stuff from part 1.
Right.
Yeah.
No, I was looking mostly at multi-agent, not single agent.
Yeah, so the easiest thing to do, and I did add utilities for all of this, is what we talked about in an earlier chapter, which is single agent reductions. And that's for independent Q-learning and central Q-learning. That was covered, here in this chapter, 5.3. And the nice thing about these techniques is that if you have like a working RL, like a single agent RL system, like package, and then you build like a multi-agent thing that you want to integrate with it, you can build a function that performs this conversion for you. So like for central learning, and I put that like in these notebooks. I have a function where like if you give it the right information, it will do the single agent reduction. And once you do that, if the package is well designed, like if not, let's say you're using like a different one, not mine, but if you have a way of converting it into the type of single agent problem that this other package would use, then you can use all the techniques from reinforcement learning to solve it.
Okay.
Like anything else.
Yeah.
And the work you have to put in is converting the multi-agent problem into a single agent problem. That is only relevant for problems that can be reduced to a single agent. Like cooperative problems is one of them.
Yeah.
And things like that. For all these other problems, that have these equilibrium solutions, you can't, like, there is no technique you can use from reinforcement learning that finds those solutions, which is why, we've been introducing all of these other techniques.
Yeah. So for the problem that I'm looking at, these agents really are working on different aspects of the enterprise, right? And they're
cooperative.
Well, there could be some sharing of information, but there's a degree of separation or autonomy into the pursuitiveness that any agent will then pursue, right? I mean, each agent, for example, that I'm using is going to have independent tools. There can't be overlapping tools, right? But they have different areas of expertise. Think of it like a production line almost, right? Where you have different people doing different things, but ultimately it all has to be integrated, right? By some orchestrator, right?
Yeah, but the overall goal is still cooperative.
Yes, but well, okay. Let me take a step. What do you really mean by cooperative in terms of feedback? In other words, an agent comes up to a conclusion X, another agent wants to change that offset by epsilon. The agent with X has the right of refusal to epsilon.
Well, it depends on not so much those details, but if in theory it's a cooperative problem, like there is a single objective that is the goal of the orchestrator, that they're trying to achieve some metric of success.
Yeah,
the details of what the agents think is important is sort of irrelevant.
Right.
Yeah. So in theory, the problem you're describing could be a single agent problem. Because again, it's the example we covered earlier in the book, where you could imagine there's an orchestrator or a central agent that has the ability to control all the sub-agents. And if that orchestrator has a single end goal that it's trying to reach, then it's a matter of deciding all of the joint actions shared between all the agents.
Oh yeah, I got it. I get what you're saying, but there are multiple objectives, though, right? Going back to the network problem, there's the interference, there's data rates, there's
So to make it an RL problem, you would have to have a way at the highest level of the problem of summarizing all the information into a single reward signal. And if you can't do that, then it may genuinely be like a multi-agent problem. But if there's something like, let's say this whole system is producing value somehow, like, I don't know, it's running a business or something, then maybe the goal is like to make the most money. And there's all like other little things that are also important, but there's sort of like, you could have the money, like if something bad happens, maybe it produces negative money in the future through some dynamics, but it would still be a matter of maximizing money. in which case you could still turn it into a single like reward signal. So it depends on the details of the problem.
I'm beginning to see there could be like a KQI, which is like a quality metric that's based on a combination of different performance metrics from each agent, is what you're suggesting, and then make the payoff based on optimizing that KQI.
I mean, a lot of like it sounds like for something over time. I mean, usually you're interested in like long-term value, and there could be intermediate things that happen along the way. I mean, usually it might make it hard for the system to learn, but the best theoretical result would be if like there's some endpoint where like you either reach the goal or you don't, and there might be a lot of stuff along the way that affects that, but you can still sort of measure success as like this worked or it didn't, and then the RL system
or it got better or it got better but not worse, you know.
Yeah, and then the RL system will sort of figure out all the like, because what you're talking about, like all that intermediate information is what should be contained in something like a value function, where it's building up knowledge of like in this state, how valuable is this or that, but ultimately it's only caring about a single like long-term outcome for the system. I mean, RL usually works better when you don't have to engineer a bunch of little intermediate things to sort of
I have to.
But then so again, without more details of the problem, I'm not sure.
Right.
It could be the type of problem that doesn't really need multi-agent techniques, like full-blown multi-agent techniques. Like it could be something
that's just like the thing.
Independent.
Go ahead.
Well,
go ahead.
Yeah, I mean, so again, like I would have to learn more
Describe
about
the problem and you determine it. Right, okay.
But depending on what's important to the problem, how the rewards are structured, it could be something where just like independent Q learning, something like that, which is essentially just a single agent method, is sufficient. Right. And of course, there are problems like if it's truly like a stochastic game, like we're looking at, where you have things where there is actually conflict between agents, or a mixture of cooperation and conflict, then it could be something where no, like you actually need like some game theory type analysis of it.
Okay.
But again,
right.
I don't know exactly. I mean, it sounds to me like you might not know how to formulate a reward signal that makes sense, but probably it's still more like a single agent problem.
Okay.
Than a multi-agent problem. Because all the stuff you're talking about is still, I mean, making it a multi-agent problem doesn't solve the reward problem. Like it just makes it more complicated. You still have to figure out like, you know, why would you want one agent to get a higher reward and have that conflict with another? Like really, it sounds like the challenge is how do you summarize
Well, they're optimizing different aspects of the output of the network. And I thought that if I just put it all into one agent, it's going to go apeshit, right? It's going to go insane. So I need to break up the problem into simpler problems that different agents have expertise in, and then approach it that way, because network has become too complex for humans, right? And so if I try to make it too complex for an algorithm, I'm going to run into the same problem. Right.
Yeah, that's kind of like the philosophy behind independent Q learning, where you don't really worry about the game theory stuff and you just sort of let each agent try to optimize its own thing.
Yeah. As I'm looking at it, each agent is going to look at other parts of the environment and run its own standard, like a single Q learning, right?
Yeah, that's what independent Q learning would do. And we could see like if you truly have a game, like a stochastic game, that it may not converge to anything.
Right.
And it's certainly not, that cannot find an equilibrium solution, like a game theory solution. But in other games or other environments, it doesn't matter because the solution is not like a game solution. It could be something that it does successfully find.
Yeah. Oh, but in my case, I think there is going to be communication required between different agents to come
that doesn't necessarily ruin independent Q learning though.
All right. Well, again, you're the expert. I'm just thinking
because
out
you
loud
can
here.
take that communication and even like put it into the state. Like it can be like you could have the agents like dump a signal to something, and that's just part of the state that all the agents can see.
That's a good point.
So like that aspect of it, I don't think changes things much.
Okay. All right.
But,
again, I'm early on in my thinking on this. And
if it's complicated, though, it sounds like you definitely need like deep learning techniques, because this is not going to be like a tabular problem.
No, it's not.
Yeah. But the good news is you can always, I mean, I haven't done it yet in the book, but there is a deep learning version of independent Q learning. It's pretty trivial to write down, and it's easy to try. Like you don't have to, it's not like it's difficult to test independent Q learning. It just might not work.
Right.
But those are the first, like the sort of early, in fact, a lot of the sort of multi-agent research or results that have been published, or, things you've seen where agents are cooperating and doing impressive stuff. Most of that work is actually, most of the success of that has been whatever model they're using and the scale of the training. They're not actually doing like a multi-agent algorithm. They're basically doing something like independent Q learning, where the agents are just learning independently. I haven't run into that much research that's publicized about like a lot of success with applying deep learning to like truly multi-agent game problems where you're trying to find, because again, like these equilibrium solutions can be very difficult to find. Like we already know that Nash equilibria are like NP hard to find. So that means that whatever algorithm you write down, however fancy it is, it's not going to beat that anyway. So like it may be able to find it, but whatever the algorithm's doing internally, like it's probably not going to find an efficient way of reaching like a Nash equilibrium, if that's what you need to find. I mean, maybe the second part of the book has some surprises in it, but even the deep learning part of the book, like I saw some of their code and examples and like interactive workshop examples involve like the level-based foraging example, which is a cooperative problem. Like it's a thing where the agents are going around, they're trying to collect items. That problem doesn't require this competitive, equilibrium type, finding.
Well, in that case that you just mentioned, are they all looking at different data related to their environment, or is there overlap in their data?
It can be all of it. I mean, you could have it where every agent can see everything. You can have a limited horizon where the agents can only see partial information. They might only be able to see partial information about other agents' actions, or, I mean, this sort of information masking can occur anywhere.
Well, I thought I would simplify the problem for each agent by partitioning the data according to their.
Yeah, you can always do that with these, even in normal, like if you go back and look at the material on single agent RL and like my notes on it, well, when you do deep learning type techniques with reinforcement learning, you have to make a feature vector. And the feature vector is where you take the state space, whatever it is. The state space could literally be any data structure, like anything. And you have to convert it into some vector which summarizes like the information. Now, it turns out this whole partial observability thing where you have some information isn't available, it's actually equivalent to all the approximation techniques that we've already covered. Because if you take an approximation technique and say, when I form the feature vector, I'm just going to leave out this information. Like the function that creates the feature vector only has access to this. That is the same as a partially observable problem. So you can just take care of that in the feature vector construction.
Interesting. Okay.
Like whatever. But yeah, like there was all this sort of approximation technique stuff like we covered pretty thoroughly in the Sutton and Bartow material. And actually the notes and code I have for that is like pretty thorough. Like it's all kind of fleshed out. So you can see all those algorithms in those notes.
Okay, great.
And yeah, you can use it. I mean, I don't know, it might be a little hard to use if you're not familiar with like Julia and everything. But actually like the code I would say, like when I write it, like it should be pretty interpretable, even like almost like the pseudocode in the book, where also like you can follow everything happening because like all the code's in there. It's not like I'm using some, weird package that has all these methods built into it from you have to study. Like it should all be in there.
Self-contained. Okay. And you've tested it and so.
Yeah. I mean, we're like,
okay.
I mean, it's all, there's working examples like
throughout
the thing. Actually, I would like, if you do want to use it, it would be helpful to get some feedback.
I will. Yeah. I need to, I would love to work with you on help to push this forward.
Because I haven't really, I basically add things that I want, based on like if I'm using it, like, oh, this would be convenient, but not so much like other people.
Well, that's why I was asking about, what's out there in GitHub and other.
There's tons of other stuff. I haven't seen any other repository that really attempts to have a really thorough collection of techniques.
Yeah.
Reinforcement.
I heard N8N, I'm sorry, has a whole bunch of agents that they've deployed on their website. Did anybody hear about that? It's a recent announcement. I haven't had a chance to go at their website, but apparently they've open sourced a bunch of different types of agents. Has anybody had a look at that yet? I'll look at it right after this call, but I mean, you get to it last couple of days.
I don't know, but I don't know if the agents, they might be talking about more like agents that use models, like language models and stuff. I don't know if it's.
I heard there was a wide variety, so I really can't say without having looked. Okay, anyway,
I don't know myself.
Okay, that's fine. All right. Hey, thank you very much. Another great session. Really love what you're doing here. I really admire your expertise and your ability to share this and communicate this information. It's phenomenal. Thank you so much.
All right, thanks. Glad you found it helpful. I wouldn't say definitely. I'm much more familiar with ordinary reinforcement learning. The multi-agent stuff is pretty new to me. So hopefully we're just sort of learning it.
You and everybody else.
Yeah, I don't know. Well, certainly, yeah, the book, it is it's a pretty new topic. So it doesn't have that much material on it.
All right. Thanks again.
Yeah, sure. If no, does anyone else have question? If not, we'll just conclude and hopefully see everyone next time.
Bye. Thank you.
Good. Okay, great.